Hi, I'm Miss Hearn. Let's get started. In this video, which is part of a series of intermediate algebra final exam review questions, we're going to work on rationalizing denominators with square roots. In particular, we're looking at numbers 39 and 12 on the review. They look something like this: 5 over the square root of 2, or 7 over 1 minus the square root of 3, something where we have a square root in the denominator. So in order to deal with these types of problems, we have a couple of important facts that we need to be familiar with. The first thing is that when you multiply the square root of a number times itself, you end up with just the number. For example, the square root of 2 times the square root of 2 is equal to 2. Or the square root of 5 times the square root of 5 is equal to just 5. You can see this because when we multiply these two together, we get the square root of 2 squared. Square root and square cancel each other out. But it's important to eventually get comfortable where you don't have to write that intermediate step and you can just go straight to 2. The other thing you need to be familiar with is conjugates. A minus b and a plus b are called conjugates because they have the same two terms, a and b, with the opposite sign in the middle. Conjugates can be any binomials. They could be x minus 5 and x plus 5, 3 minus 4a and 3 plus 4a. As long as they have the same two terms with the opposite signs in the middle. But in this case, we're going to be looking at conjugates that have radicals in them. For example, we might have 3 minus the square root of 5 times 3 plus the square root of 5. These are also called conjugates. The reason why conjugates are important is because when you multiply conjugates together, you get a difference of squares. For example, x minus 5 times x plus 5 turns out to be x squared minus 5 squared. You can see that by FOILing it out, and you'll find that the middle term cancels. So we would say that that's equal to x squared minus 25. Or 3 minus 4a times 3 plus 4a, that turns out to be 9 minus 16a squared. 3 squared is 9, and 4a squared is 16a squared. But it also works when you have square roots. 3 times 3, 3 squared is 9, minus the square root of 5 squared is just 5. So this turns out to be 4, which doesn't have a square root in it anymore. So there's two situations where the square root cancels out. One when you multiply a square root times itself, and one when you multiply on a pair of conjugates together. So let's look at some examples where we can use this idea. There are two cases that we're interested in. Case 1, we have a fraction with a radical in the denominator, but there's no addition or subtraction. For example, 6 over 5 root 3. In this case, we're going to use the fact that if we multiply the square root of 3 times itself, the square root will go away. And what we're going to use that fact to do is to rewrite this number in a different way without changing the value so that there's no square root in the denominator. That's called rationalizing the denominator because a square root is an irrational number. We don't want to have an irrational number in the denominator. So in using the fact that multiplying a square root times itself gets rid of the square root symbol, we're going to multiply by square root of 3. But we can't just multiply it because we want to. What we can do is multiply square root of 3 over itself, which is really 1. You can multiply a number by 1 and not change the value of the expression. In the numerator, we would have 6 times the square root of 3 is 6 root 3. And in the denominator, we would have 5 root 3 times root 3 is going to be 5 times. Now remember, square root of 3 times square root of 3 is just a 3. So this is 6 root 3 over 15. But anytime you are working a problem that has a fraction in the answer, you need to make sure you reduce it completely to lowest terms. What goes evenly into 6 and 15? Well, 3 does. 3 goes into 6 twice, and 3 goes into 15 5 times. So This is equivalent to 2 root 3 over 5. Now 2 and 5 are both primes. They definitely have no factors in common other than 1. So we've reduced to lowest terms and we're done. Now let's take a look at item number 12, 5 over 8 minus the square root of 3. Again, our goal is to rationalize the denominator. In other words, get the square root out of the denominator so that we have a rational number in the denominator. It might be tempting to multiply by square root of 3, but if we do that, when we multiply square root of 3 times itself, we get 3, which is good. But when we multiply it over to the 8, when we distribute, we're going to get 8 root 3, which means we would still have a square root in our denominator. So that's not helpful. So instead, we're going to use the idea of conjugates. We're going to multiply 8 minus square root of 3 times its conjugate. Remember, conjugates are the same two terms with the opposite sign in the middle. So we would multiply it times 8 plus the square root of 3 in the top and the bottom. This way we're only multiplying by 1 and we're not actually changing the value of the expression. So let's see what we get when we multiply this out. We're going to have 5 times 8 plus the square root of 3. I'm not going to multiply it through yet. I'm not going to distribute yet because we might need to reduce. And if so, it's easier if it's already in factored form. Now I'm going to multiply 8 minus square root of 3 times 8 plus square root of 3. Remember, when you multiply conjugates, the product is a difference of squares. So in this case, we would have 8 squared minus square root of 3 squared, which is going to be 64 minus 3, which is 5 times 8 plus root 3 over 61. Now at this point you would check, do 5 and 61 have any factors in common? Nope, 5 doesn't divide evenly into 61 and 5 is prime, so we definitely cannot reduce. So we could go ahead and distribute the numerator, 40 plus 5 root 3 over 61. And we're done. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the video.